हमें स्टार्ट कर रहे हैं ना?
Okay, greetings from ARIES Nainital. You can see on the you can see there, that's our institute, Nainital, ARIES, over a hilltop called Manora Peak. So I will be talking about black hole astrophysics today, but it will be in a very I should say it should be in the comfort level of undergrad students and postgrad students, not for basically for the experts. So I'll just go around what is basically black hole astrophysics, try to give a broad a description about black hole astrophysics. So there will be a general introduction of black holes and what do we mean by astrophysics around it, and then a brief introduction about GR and black holes, because I presume that GR is not really taught in the undergrad classes, but again it will be in a very basic level. Then again, so I'll go about what is black hole astrophysics and various aspects of it, and then I'll summarize this talk. So astronomy is the science which studies the universe which is beyond Earth's atmosphere, while astrophysics is a branch of astronomy which explores the physical processes associated with various celestial objects and various celestial events. Therefore, black hole astrophysics is the study of physical processes around black holes. So why do we need to study black hole astrophysics? Firstly, the surrounding of black holes is a very extreme situation where magnetic fields can be very high, temperatures can be extremely high, the velocities will be very high, the densities might be very high or low depending on what is going on exactly there. So it is a very extreme physical scenario, and we have to understand various physical processes that goes around a black hole, and in a way one has to also detect black holes using this black hole astrophysics as a subject. All right, research in astrophysics is similar to detective work because it's everything that is happening is beyond our control. We don't know anything about what's going on. And what happens is that we find some evidences that has happened. Okay, so the sudden burst of light or sudden we see a certain light coming from somewhere, and then suddenly there's a change there. So it's like like a detective. The crime is done before the detective enters the scene, and then he or she builds up the story, accumulating all the evidences of the crime act, the criminal act. So these telltale signs for astrophysics, or these evidences of astrophysics, is like collecting data. So we can now, at this moment, we can really broadly divide it into two. First is the traditional one, that is collecting electromagnetic signal from various energy range from various celestial objects. That is basically capturing light in all energy ranges, for example, from radio to gamma rays. And a new branch has emerged for the last 3-4 years with the successful detection of gravity waves by the LIGO experimental consortium. So these are the two. I will not be talking about gravitational wave astronomy. It has now entered into the astronomy domain because there are many detections, because that will take a lot of time and it warrants a separate talk for gravity wave astronomy. I'll try to focus only on the first part, the traditional astronomy. The black hole astrophysics that depends on traditional astronomy, that is basically collecting electromagnetic signal. So, so the instruments to collect data in traditional astronomy are basically telescopes, and they range from radio to X-ray. I have just given 6 examples of it. The radio, like VLBA, is a very large base array of radio telescopes. You can see those dishes there. That is there, this VLBA. And of course, you have our own GMRT, which is in near Pune. In the optical, we have the biggest telescopes at the moment, which is the Keck telescopes. There are two Keck telescopes there, and there's the Indian largest telescope we have, that is Devastal Optical Telescope, 4-meter glass telescope. We have it in ARIES. And again, there is a X-ray Chandra X-ray telescope, and here is the Indian one, which is the AstroSat. So we use all these instruments. These are all, of course, satellites. These are satellites. These are ground-based. This is also ground-based. We know that X-rays and gamma ray. I mean, X-rays you can't really see anything beyond ultraviolet because Earth's atmosphere blocks them. So we need to put them in satellites above the Earth's atmosphere to collect data in X-rays and so on. All right, and gravity wave astronomy is essentially at the moment LIGO collaboration, which has laser interferometers. So you have two there, and gravity waves, I can just touch upon it. What gravity waves does, it changes the space-time. It's very tiny amount, but it changes differentially in the sense that if it is elongates the space-time in one direction, it will elongate. It will contract the space in the other direction. So if you have two laser beams going perpendicular to each other, and you interfere them, and when a gravity wave passes, then one of the arms will be shortened, another one lengthened. So it will the path difference will change when they interfere. So that's how the gravity waves are detected. But anyway, I will not be going into details of that. All right. So what are black holes? Now, black holes are quite popular now because essentially of this picture there, it's a image taken by Event Horizon experimental experiment. It's again a consortium of many scientists. It is the image of the heart of an elliptical galaxy called M87, and what we see here is what is called the shadow. This black region is called the shadow, and this region is the light. The wavelength of the light is 1.3 millimeter, which is it's one can say not exactly in the radio range, just what should I say, ultra radio or something. So 1.3 millimeter. It was chosen because that's the wavelength which can reach us from that distance, almost without interacting with any other intervening medium. So, it's very popular. Or, for example, Nobel Prize of 2017 was bestowed on three people here who led the LIGO consortium. They detected gravity waves emerging from black hole merger, and it's Kip Thorne there. Receiving the Nobel Prize, and two black holes merging there, and the two black holes, when they merge, they disturb the space-time around it, and that the disturbance travels as a wave and reaches us, and that's what they detected. So we know the almost textbook level of definition, school book level of definition of black holes. Almost everybody at the moment knows that there are three types of dead bodies of stars. The lighter star ends up as white dwarfs, where the stellar remnant is supported by the electron degeneracy pressure. The heavier stars again are called neutron stars, which are supported by neutron degeneracy pressure. But still heavier stars end up as black holes because there are no other pressure that can hold the gravitational collapse. And black holes are black because the gravity is so strong that not even light can escape. Again, these are all easy definitions. In astrophysics, the black holes comes in roughly in two mass range. One, it's around few solar mass to tens of solar mass, and others are like millions to billion times heavier sun. So these supermassive black holes, which are the million to billion times as heavy as sun, are generally found at the centers of galaxies, while these stellar mass black holes, these ones, this few tens of times heavier than the mass of the sun, are found in various binary, like extra binary is what we call it. It is so the one of them is a black hole, the other one is a normal star, and the normal star feeds the black hole with matter, and then they glow. The matter, when it falls into the black hole, they glow and they emit in all sorts of wavelengths. Okay, so because it is intended for the students, I will just touch upon what is GR in a very what should I say, in a very pedestrian level, I would say. So we need understand general relativity to in order to understand what are black holes and how matter should behave around black holes. So Albert Einstein postulated the edifice of relativity, that is a special relativity, in 1905, and then for around 10 years he worked on to give a description of relativistic gravity, and in 1915 he proposed the structure, or the mathematical structure of general relativity. So we have two aspects here, relativity and gravity, and we will try to understand both in simple terms. First, Newton's gravity, because we have to start from Newton's gravity. It is better to remember that Einstein actually never negated Newton's gravity. He actually gave a newer description of Newton's gravity. So one can say Einstein dressed up Newton's gravity in the form of special relativity. So that's a better way of describing GR. So what is Newton's gravity? So the formulation, Newton's formulation gravity, was the result of many astronomical observations and people who worked with, especially Kepler. Kepler's laws actually helped Newton actually formulate this 1 by r squared form of gravity. So essentially what that famous incident of the apple falling onto Newton's head, and Newton discovered gravity. I mean, what did he discover? What he discovered was that the force with which the apple fell onto Earth is also the force with which the moon is rotating around Earth. So therefore, the centripetal force of the moon is equal to the Earth's gravity. Okay, and then he used Kepler's third law, which gives the t squared proportional to r cubed into the v squared by r form of the centripetal force, and from there he actually obtained the 1 by r squared, this 1 by r squared dependence of the Newtonian gravity. Now, so it was very successful in the sense that if you remember your high school level physics or early bachelor level physics, then we know that the effective potential of a Newtonian gravity is like minus 1 by r plus L squared by 2r cubed, L being the angular momentum, specific angular momentum. Here I put G equals to M equals to 1 in some unit system, okay, not in the physical unit system. And if you plot this, then we find these effective potential, if you remember them. Okay, so this is for one angular momentum, this is for another angular momentum, this is for another angular momentum. And the circular orbits where we find the minima, okay, that will be the location of the circular orbit. But if the energy of the particle is around here, then it cuts this effective potential for this angular momentum at two places, right? So this is like the perigee, that's the location of the perigee, and this would be the location of the apogee. G means geocentric. It would be perihelion if it is if you're talking about motion around sun, and so on. Pericenter and apocenter is a better word. So if the energy is here, we will be talking about an elliptical orbit, and all the satellites all the planets around Sun, they follow this elliptical orbit, and everything was fine in Newton's as far as Newton's gravity was concerned. So that it explained the motions of planets and satellites. Now there were no problem. There were two philosophical problems for Newton's formulation of gravity and one observational problem. So the two philosophical problem is that in Newtonian mechanics, so you go back a little bit about in physics, take your physics textbook up and go back. In Newtonian mechanics, the force is proportional to acceleration, and the constant of proportionality comes out to be the mass, and we call it inertial mass. Okay, so this inertial mass. In Newton's gravitation, force is proportional to the mass, and for uniform gravity, the proportionality constant turned out to be the gravitational acceleration. So there is no reason why mg, or the gravitational mass, and the inertial mass has to be equal. But experiments after experiments, starting from 1700 till to date, shows that inertial mass is exactly equal to the gravitational mass. Why? It should not be. In Newton's formulation of mechanics and gravitation, though these two masses appear at different places and they have different roles, why should they be equal? But yet, experimentally, they are equal. It was a philosophical problem in Newton's times as well. So that was one problem. The second problem is Newton's gravity is instantaneous. That is, if today I move Sun from its position to some other position, by the formulation of Newton's gravity, it will affect infinite distance instantaneously. While Einstein postulated the special theory of relativity, it tells us, special theory, I will just touch upon it a little bit later. Special theory of relativity tells us that there is no physical information which can, travel faster than the speed of light. Okay, so this is again a philosophical problem. Nobody is worried about it. But some people were worried. Einstein, one of them, but not many people were worried about it. And the third problem is the perihelion shift of Mercury. Although the planetary physics was pretty good using Newton's laws of gravity, but for Mercury, astronomers found that the perihelion of the Mercury shifts very slightly, extremely slightly. It's, I think, about 1.43 seconds per century. So, but it does shift. And people did not know why, because according to Newton's gravity, if you can just go back. So if you have an effective potential like this and the energy of the particle is negative or less than the rest mass, then it should in general give a elliptical orbit. There is no two ways about it. However, and therefore the perihelion shift should not be there. So people understood if the 1 by r square gravity changes slightly, then one can describe why the perihelion shift. So people assume that there are many astronomical objects, maybe they are interfering with the 1 by r square of gravity of the Sun, and therefore this coming out. It was not a big problem, but it was kind of an annoyance, this perihelion shift of Mercury. And Einstein was not even bothered about that. Okay, so now special relativity. Again, a nutshell. I will not go into the details, though it's not also possible to go into this, all the space-time figures and so on. So what is special relativity? In a nutshell, it is about the measurement of positional time of occurrence of any event, whatever that event might be, by different observers. Okay, so if different observers separated by, differentiated by of their velocities, relative velocities, then, and if they want to describe the same event, these two observers, then what should they measure? Okay, so that's all about special theory of relativity. For example, if you're running after a car, Okay, so this is you, and this is the car. You're running after the car, and there is a bystander there. Okay, so somebody standing on the street. That fellow says that you are running with a speed v, and the car is scooting away and with speed u. Then, if that is the speeds measured by bystander, then our Newtonian mechanics tells us that the car speed is u minus v with respect to u. Okay, if you measure the car speed, it will be u minus v. This is Newtonian mechanics, and the transformation what we have done here is called Galilean transformation. The assumption here is that the time taken for you to get the information of car, that the car is moving at this point, at this time it is there, and the time taken for the same information to go to the bystander, irrespective of your velocities, relative velocities, is exactly the same. That is not the case. Okay. In other words, time taken by light or any information from the car to reach you and the bystander is instantaneous. It reaches at the same time, or takes no time at all. That's the assumption that is that's going there. Now, there was some problem with Maxwell's equation. I mean, one can go on and on and on about why Maxwell's equation and Newton's mechanics is not correct. I mean, not what should I say? Not congruent to each other. But just one thing I will just mention here, that in Maxwell's equation, if you use the Maxwell's equation, especially the advanced level bachelor students knows this, that you can manipulate the Maxwell's equation in the form of a wave equation. If you do that, then this wave speed that comes, it comes out to be the speed of light in vacuum. You can consider any observer, any damn observer, that the speed of the wave comes out always to be light speed in vacuum, independent of the frame of reference. So it suggests that the speed of light is a universal constant, and do not follow the transformation made here, right? If this is the transformation here, then the speed of light measured by this fellow and this fellow should be different. It should be u minus v, right? But not so. It is always c. So taking a clue from this, Einstein postulated that nothing can move faster than the speed of light. That is pure genius by Einstein. And the maximum upper limit of the speed, and it is the maximum upper limit of speed of any physical information. Okay, and then if you do that, you can show that the time intervals and space intervals are not invariant. In Newtonian mechanics, we separately take it to be invariant. For example, if I take this and throw it, then the person who's sitting here will measure this length, and I will be measuring things same length of this particular object. That is not so. Okay. So even the time intervals, like if my watch is giving 1 second, then if somebody is sitting on sun will not see the 1 second. I call it to be 1 second. Okay. But the space-time interval. So is a time interval and this is the space interval. This space-time interval is invariant if c is constant. It can be shown mathematically. Now, so basically, if the fact that the time interval and the space intervals are not invariant is actually translates into the length contraction and time dilation. Okay. Now, so both the space and time coordinate transforms, and this transformation is what is called Lorentz transformation. Again, if this is invariant, from here you can derive Lorentz transformation. Absolutely, absolutely bona fide calculations. And no physical information can move faster than the speed of light. So consequently, the velocity addition law that we mentioned, it will not be u minus v, but it will be like u minus v by 1 minus uv c squared. It can be shown. Okay. And because no physical information can travel faster than the speed of light, so the gravitational interaction cannot affect instantaneously at large distances away from us or from the source or a star. Therefore, Newtonian gravity violates special relativity. Okay? All right. So let us proceed to build a relativistic gravity. Okay? And to do that, we focus on some peculiarities or some properties, not say peculiarities, of gravitational interaction, already noticed by some stalwart scientists, notably by Galileo. What did Galileo's experiment from the Leaning Tower of Pisa show? It showed he dropped to a heavy object and a big object, and then he dropped from this to Pisa, and he found that both of them falls at the same rate. Okay, so therefore, in Earth, if you fall and an apple falls, assume it to be an apple, falls, both of them will fall with the same acceleration g. Okay, we all know that. Now, forget about this. Let us talk about lifts. Okay, by the way, this is what is called Einstein-Gedunkin experiment, okay, or thought experiment. So let's talk about the lift. And the lift is moving up with an acceleration g. And the person inside the lift will see that he is being pulled down with an acceleration g, and the apple is also accelerated downwards with g. Therefore, if you have two persons, one person inside a room in Earth and a person inside a lift traveling with a speed with an acceleration g upwards, there is no way these two persons can say that which one of them is sitting in a lift or which one of them is sitting in Earth. Other words, observation 1, no difference between uniform gravitation and uniform acceleration or accelerating frame. Therefore, like pseudo force, the gravity can be removed by frame transformation. Uniform gravity can be removed by frame transformation. That's exactly what we see. If we fall down, we feel weightless, right? Okay, that is exactly, now I am feeling the weight, I'm sitting here, but if I fall, I'll feel weightless. And people who have traveled in air, when there's a bump in an airplane, then when it falls down, you feel giddy, right? You feel weightless. That's exactly what's going on. Okay. Observation 2. Now, if we accept that uniform accelerating lift is equivalent to a room of in uniform gravity, so assuming C to be constant, again assuming special relativity to be valid, then now if I shoot light, if the lift is at rest, it will hit parallel to a point there parallel to the floor of the lift, right? If it is moving up with a constant velocity, it will not hit that B point, it will hit somewhere B prime, but this distance is the distance that the lift goes up, and in time t with constant velocity, the distance going up will be Vt. So again, if you plot this trajectory of light, it will be a straight line. But if it is moving with constant acceleration g, then in time t, it will not go Vt, it will go half gt squared, right? Okay, and if you actually plot here, then this turns out to be a parabola, right? So from this thought experiment, Einstein postulated that gravity bends light. And we know that two positions, the shortest distance between two points is a straight line. Why? Because light travels in straight line between 2 points. Light takes the shortest distance between 2 points. So therefore, if the shortest distance between 2 points in uniform acceleration or in uniform gravity is bent, then the space-time is bent, is curved. So gravitational field is the manifestation of the curvature of space-time. Einstein concluded from this thought experiment. Okay, you see, no fancy mathematics. Fancy mathematics comes later when you postulate the GR. Now, a variation of Einstein's third observation, Galileo's experiment. Galileo, I mean, if we put two poles and drop two heavy objects very close by, put the two poles close by, then they both of them will fall with the acceleration g, right? And so one is sitting here, the other is sitting there. If they look at each other, then they will be saying that both of them are not moving with respect to each other, or both of them are inertial observers. However, on Earth, if we take this pole at two very large distance away, then the Earth curvature will come into play. And although locally they are falling with g, this fellow will see that this person is coming closer and closer to him. So initially they were static, and then this fellow will see it is gaining some relative velocity towards him. In other words, then it is not inertial observer. So therefore, although uniform gravity can be transformed away to an inertial observer like this, but universally you cannot do that. Globally you cannot do that. You cannot take one inertial observer and replace gravity altogether. And therefore, gravity is not a pseudo force globally. All right. So that's what. So this is essentially the principle of equivalence, the famous principle of equivalence, based on which the general relativity was developed by Einstein. Okay. So what Einstein did was, he did not want to generalize Newton's gravitational law, but what he did was he generalized the Poisson equation. Okay, remember the Poisson equation? So he did that, and the source in Poisson equation, the source of gravitational potential was density, mass density. Here it will be energy momentum tensor, because it's relativistic. All form of energy can gravitate. Can behave like mass. So after a lot of years working, so this is a generalization of Poisson equation, and this is called the Einstein field equation, and it was proposed in 1915. And this is the field, or this is the Ricci tensor, this is the Ricci scalar. G mu news are the metric tensor component. So you see that we wrote the special relativistic thing was like ds square minus cdt square plus dx square and so on. Here there will be g mu news, and the g mu news are not constant now. In case of special relativity, these are -1 and +1 +1 +1. So these are not constant. They will depend on the coordinates, the x mu's and x mu's. Okay. So, and g mu news was shown, they actually store the information of curvature and therefore the information of gravity. Okay. All right. So that's what I said. The g mu news stores the information of gravity. I just swept few decades of research in one slide. And Einstein never thought that his field equations will be anyone will be able to solve it. But the very next year, Karl Schwarzschild, he was a German soldier in the trenches of First World War. He actually got some time and he solved it for spherical distribution of matter. And this is the space-time element that Karl Schwarzschild obtained, and describes the surrounding of a spherical star, something like our sun. Of course, the sun is not compact enough to show GR effects. If it was compact enough, it would have shown these GR effects. But it does in a slight, in a very perturbative way. So now, again, now I'm just going a little bit faster here. So now, if the matter, this M, can be confined in a radius which is less than 2 gm by c squared, then this term goes to 0 and this term blows up. Okay, that term, that distance, Rg we call it, is called the Schwarzschild radius, and it is what is generally called the size of a black hole, or the radius of a black hole. So any matter that goes inside this 2 gm by c squared, or Schwarzschild radius, then that matter becomes a black hole. Why? Because whatever light that matter might be emitting on the surface of this sphere, imaginary sphere of radius 2 gm by c squared, the escape speed comes out to be the speed of light. Okay, and therefore nothing can come out. So therefore it's called black hole because it's black. And so any matter entering the black hole enters with the speed of light, and black holes do not have hard surface. Okay, because it's imaginary surface. And matter entering into black holes has to be subcaplarian. What do we mean by that? I'll just come to that now. And fundamentally, final goal of black hole astrophysics proving the existence of horizon. Okay, all right. So a black hole cannot be seen. It can be seen or detected. Therefore, by studying, okay, so there's some error here, typo error. By observing the matter moving in the space-time around the black hole. Okay. Okay. So black hole astrophysics 1. It's the stellar motion around a black hole. Okay. So studying the stellar motion around black holes. So if the stars are generally, especially this happens if a star is moving around a supermassive black hole. So a star would be like tens of solar mass or maximum hundreds of solar mass, while a supermassive black hole is million solar mass or billion solar mass, and therefore the star will not affect the space-time of a black hole. Okay, it's too small. So then we can treat that star as a free particle, and the equation of motion of free particle in general relativity is called a geodesic equation. Okay, so it will be following this curved space-time. So what Einstein said that planets around Sun is actually not moving in a ellipse governed by the force of gravity, but it is moving around the elliptical path as the space-time around Sun. The Sun's gravity has actually curved the space-time in a way that is the path allowed for Earth to move around, and therefore an Earth is actually not moving in a force field. It is actually freely falling in Earth's gravity, and that is why the mass, the inertial mass and the gravitational mass is not different, because gravity is no force. Okay, all right. So anyway, so the equation of motion of free particle around in a gravitational field is given by this, where p's are the 4 momenta, g mu nu you know is the metric coefficient, p nu this p is called an affine parameter. It is proportional to the space-time element s that we saw before. Okay, this s. All right. So relativistic Kepler problem, from the geodesic equation, if you sort of do a little bit of algebra, then you can find out for massive particles, this is the 4 velocity expression of 4 velocity. This is the energy, which is basically u sub t. Okay, I'll not discuss that. This is the energy, specific energy of the particle, which is a conserved quantity, and this is the specific angular momentum. L is specific angular momentum of that particle, which is again a conserved quantity. You can show when it can have a conserved quantity by applying the Noether's theorem. But anyway, I'm not going into details of that. So, and this part is the effective potential. Okay. Now you see, it replicates the Newton's gravity. This 2 by r is 2 gm by c squared. Okay. I have put g equals to m equals to c equals to 1. So this is the gravitational potential, what we know, right? 1 by r gravitational potential. This is the centrifugal potential, a centripetal potential, right? So L squared by r squared. Okay, but you have also a third term, that is 1 by r cube. If you multiply it, you have 1 by r cube. That is the general relativistic correction. Okay, and that does a lot of things. First, the effective potential now goes to 0 at r equals to 2 at the Schwarzschild radius. Okay, and in the Newtonian case, you saw that you have only minimas. Here you also have the maximum. Okay, now again the minima is the location of circular orbits, stable circular orbits, and the location of maximas are the location of unstable circular orbits. This is, we are talking about massive particles, that is the mass is not zero, or it's not, we are not talking about photons here, we are talking about a star around a black hole. Okay, so but again, like Newtonian mechanics, if the energy of the particle of the star is slightly higher than this minima for this angular momentum, it will cut at two places, and one of them will be pericenter, the other one will be, where is it? Yeah, the other one will be the apocenter. Okay, so this is the pericenter and that's the apocenter. And because of this 1 by r cube term, now you don't have an elliptical orbit. You have an elliptical orbit, but after completing the ellipse, it never comes back to its position. It moves slightly different. So therefore, it is like shifting. So if you're moving like this, and then it will go like this, then it will go like this. So your pericenter is shifting. Okay, all right. So at one go, Einstein gravity, although it did not want to address the perihelion shift of Mercury, but it could explain it absolutely correctly. But this is also a case of star motion around the black hole. So if the black hole is somewhere here and the star is moving, its orbit will be shifting like this. Okay, so it starts with red and then it goes like that. All right. So applying it to, so that's what we said here. This r cube terms gives this perihelion shift. Not perihelion, it should be written pericenter shift. Okay, perihelion is around the sun. Okay, so applying it to our solar system, that's what I said, the Mercury perihelion shift was explained. But this is also applied on stars around the supposedly black hole at our center of our own galaxy, Milky Way. And all the stars are studied, especially this star, this S2. Okay, and it comes very close to the black hole. I mean, this perihelion is close to few Schwarzschild radius, and it still follows exactly what GR predicts. And there was one paper recently by Andrea Ghez, and Andrea Ghez was very disappointed that even here the GR is predicting correctly. Had GR not been predicting correctly, then there would be an opening for other relativistic description of gravity apart from general relativity. Okay, so that's one black hole astrophysics, one type of black hole astrophysics. Let's go to black hole astrophysics. Type of black hole astrophysics people do kind of the second kind. It's the light bending effects and photon orbits and so on. The geodesic equation, as we talked about for material particles, can also be written for photons. Okay, and then if you just do a little bit of algebra, it comes out to be 1 by b square. B square is actually the ratio between the photon energy, specific energy, divided by photon specific angular momentum. But it basically is the impact parameter, and V photon squared is the effective potential for photons. Here, and again for photons as well, we have an extrema. However, it turns out to be a maximum. Okay, if you plot the photon potential, then it turns out to be this. So now, if the impact parameter is less than the critical impact factor, the critical impact factor is the impact factor corresponding to the maximum. Okay, if it is less than that, it will be captured. The photons will be captured by the black hole. If it is greater than that, then it will be an unbound orbit, and it will be some sort of a parabolic or hyperbolic orbit, depending on what energy and angular momentum you have. Okay, and so here, we are shooting photons from, I don't know how much, 5 gm by c squared. So this is the black hole, the shaded region, and shooting photons from here with various impact parameter. You see with the blue one, it starts to rotate. Okay, So it's a photon orbit there, this blue, and because it is unstable, some of them also go out. Okay, it's unstable, right? It's not going to stay there for, but at least once or twice it rotates, and their impact parameters less than the critical impact parameter is eaten by the black hole, and the rest goes out. Here, this one is higher than the black impact critical impact parameter, and it's bent, but it goes out. Okay, and I have done it repeated for various injections. Okay, and if you do it for many cases, you will see that the photons within that impact parameter, this is BC, the critical impact parameter. On one side, it is around 2.5 gm by c squared. The other side is also 2.5 gm by c squared. Sorry, 5 gm by c squared. So it's around this 5 gm by c squared radius. Any photons that have emerged outside the black hole will be eaten up by the black hole. The rest of them can go out. So if you're looking from here, basically, so that's what you will see. So you'll see some sort of a photon orbit there, and then the halos go out and out, and inside you will have this around 5 gm squared size of a dark region. This is exactly what was measured in the EHT, or the Event Horizon Telescope telescope experiment. This is the region we are talking about. It matches with the gravity. However, because the number of the baseline array, it had the number of telescopes they used is just 8. So it is, the resolution is a little lower. If they increase the number of dishes, then it will increase. Okay, but so that's what the EHT did. One needs need a full talk to do justice to EHT experiment, but I'm just it's a sort of a overview, so I'm stop here. Then the black hole astrophysics 3, that is accretion disks and jets. One should say that EHT 2, the black hole astrophysics 2 and 3 are also related, because in the sense that the radiations are generated from accretion disks and black holes and jets. So that has to be there. But anyway, we can talk about accretion disk and jets separately as well, because not all black holes are suitably, at a distance where we can actually resolve the horizon region. Anyway, so astrophysics has two very important components. That the matter, when it comes close to the black hole, because of the very strong gravity, it compresses the infalling matter and it heats it up. And what happens, these individual matters smashes up in the form of a fluid, and they form an accretion disk. They form accretion disk. Why? Because if they have angular momentum, matter with angular momentum tend to be on the equatorial plane. Okay, so therefore it's a disk, but it not always looks like a disk. Okay, so but it's a sort of a generic term, accretion disk. Okay, and it's, the matter is so hot that it's the form of plasma and radiates in the form of radiates in the wavelength from radio to gamma rays. Okay, and part of the accreting matter is also ejected in the direction perpendicular to the accretion disk plane. There is no consensus about the exact mechanism to generate this jet, but we do see it. Okay, I mean, we do observe it. And one important point: the matter in accretion disk and jets are in fluid state, and that cannot be described with geodesic equation. Therefore, it is no more a free particle. It is an interacting particle. It's interacting a bunch of particles, so they do not follow geodesic equation. They actually, you have to have a relativistic version of an Euler equation or a Navier-Stokes equation in presence of magnetic fields or in absence of magnetic field, as the case might be. Okay. So observation and phenomenology. In 1950s, strange point-like objects, a little bit of history, are discovered, which are very luminous, cosmological, and the spectra is not like a star. They were called quasi-stellar objects, now called quasars or broadly active galactic nuclei. And the luminosities are very high. It can go from 10 to the power 44 to 48 Hz per second. And the spectra mainly non-thermal. It has consists of non-thermal components. And the mass required to obtain such luminosity would be around, not the mass, the accretion rate rather, the supply of mass is 10 to the power 6 to 10 to the power grams per second, which would require millions of stars at the center if it has to be generated by only by nucleosynthesis. Okay. So, and if it's so much mass is there at the center of the galaxy, then we should be seeing it, but we don't see it. For example, center of Milky Way galaxy, it's around 10 to the power 6 m sun, okay, or solar mass, but we don't see it. Okay, this is somewhere here it is there. To the best of our resolving power telescopes, we don't see it. So assuming a black hole mass, again, if we can track a star or a gas motion around it, and we can track one emission line, then what we see is that one part of the emission line is redshifted, the other is blue shifted, which tells about its rotation. And applying the Kepler's law, we can find out what's the central mass, and that turns out to be very high, and we don't see it. Therefore, these are all black holes. And as we said before, black holes falling into black holes speed up and also heats up, and so they emit in higher energies. Oops, sorry. Okay, sorry. Where was it? Yes. All right. So the spectra, what we see is that generally the spectra is in two states. One is called the low hard state, which is the power is maximum in the hard. This is a spectrum. Okay, this is frequency, and this is the flux and flux of radiation. And we see that it peaks in the high energy part, and it's non-thermal. You can see this non-thermal part, this power law part, and this is called the hard state, but they are low luminosity. The spectrum is peaking around the high energies, but it's low luminosity. Also, we can see a thermal component of it, but it is not dominant. Okay, that's called the low hard state. It's also the high soft state, dominated by thermal photons, and so it's a high soft state. It's the power has shifted to the lower energies, but the luminosity or the brightness has increased. Okay, so it's called, that's why it's called high. It's luminosity high, but soft state. The spectrum is soft. Okay, so you see a weak power law here. It's a strong, it's a dominant power law. It's a weak power law. And in the hard state, and in between hard and soft, there are many intermediate states. And in the hard to hard intermediate states, we see highly relativistic jet ejection. This is SS433. It is not highly relativistic in this particular case. It's around 26% the speed of light. Matter is being ejected. So this is called SS433. But there are cases where it can eject at 90%, even 99%, with Lorentz factors, few tens of Lorentz factor as well. Okay, so that jet is there, and this is, again, we come to M87. The jet outflows, the divergent flows, so colder, emits in optical IR. So the accretion disk in higher frequencies, the jets in lower frequencies. Because it is expanding, so it's getting it's cooling down, and therefore it's emitting in lower energies. So this is a jet of M87, the one with in the EHT experiment, and the jet is being launched from very close to the black holes, around few tens of Schwarzschild radius around the black hole. So it's very close. So you can see this arm is around 1.5 kiloparsec, and this distance is less than it should be. If we take it around 100 Schwarzschild radius, if it is 100 Schwarzschild radius and 10 to the power 9, means it's around 10 to the power 7. Say around a parsec or so, a little more than parsec distance. So something which is being generated less than a parsec region is traveling kiloparsecs. Okay, and the speed of these objects are are very, very high. It's around the speed measured is around 99% the speed of light. Okay, and then again in the spectral states, when there is a hard state, that is, it is dominated by a power law, then these photons also shows a quasi-periodic oscillation. Okay, now if you do an FFT of this power law photons in the power density spectrum, it gives a peak. You understand what is an FFT? It's fast Fourier transform or Fourier transform. For example, if you have a sine wave that is in the time and x-axis and domain, right? Time and space domain. Now, if you go to the frequency domain or the energy domain, then you get the power in the energy domain. Okay, and if you get for a sine curve, if you do a Fourier transform, you get a delta function. Okay, so therefore it is a pure sinusoid, and or in other words, the purely a periodic motion. But if you don't get a delta function, but there is a peak, but it's a spread. There is a spread. Okay, then what you call is a quasi-periodic oscillation. So therefore, the whatever that is generating this power law is also oscillating, but not exactly periodically, quasi-periodically. That's what we see here. And this quasi-periodic oscillation evolves in time. So this is again a Nature paper by Mirabel and Rodriguez way back in 1999, which shows that when the accretion, this black one is X-rays coming from accretion disks. When the X-rays dip, you start to see the jets. Okay, when the X-rays dip means, and the hardness ratio goes up. This is the hardness ratio. Hardness ratio is the number of hard photons with respect to the soft photons. Okay, so the hardness ratio goes up and the luminosity goes down. You start to see these ejections. Okay, and they evolve in time. Initially, it is like low hard state. Most of the time, they want to stay in the low hard state, and then there you see very weak jets. But then, as it increases, the luminosity increases. It is going from low hard state to intermediate hard states. The QPO also increases. The jet also strength increases, and then before it goes to the soft state, it ejects relativistic ejections. I mean jets with Lorentz factors greater than 2, few, or sometimes it is 10 or more than 10, and then goes to the soft state. When it goes to the soft state, it is dominated by the thermal emission, as we said, and no jet, no QPO. Okay, so so that's what we know. Various disk models. One must understand that fluid mechanics, magnetic or otherwise, is a set of nonlinear equations, very difficult to solve, and it was not properly solved till 1950s. Okay, so the first accretion model was given by Bondi in 1952. He tried to he solved radial matter falling into a gravitating center here. Okay. And for black holes, people thought that this should be the dominant mode of accretion, because black hole is super attractor and gravity is by and large spherical, so it should be spherical accretion. That is, spherical means radial, it's coming from all sides. But it was shown by many people, Shapiro and many other people showed that if it is falling directly like this, it stays it stays outside the black hole far too small time, so that it cannot really generate a lot of photons, and the luminosity of these if these accretions are very low. And then it went to the other extreme, that Keplerian disk, Sakura Tsunaev, Novikov-Thorne, Pringle, and many other people, they went to a Keplerian disk. That is, so people understood phenomenologically that you have to make this matter before falling into the black hole to stay there. And how to stay? I mean, it has to move in close to a Keplerian orbit. So they assumed a Keplerian disk, that there is an accretion disk where there is very low radial inflow. Mostly it is rotating almost in Keplerian angular momentum, and the viscous dissipation is generating a lot of heat, and they are and because a lot of matter is accumulated on the equatorial plane here, so it is optically thick, and they are making locally they are producing black bodies, and the total luminosity will be sum of all these black bodies here, and they will get a modified black body spectra here. So that's the thermal origin of the spectra. And they proposed it. It was successful in the sense they could explain this thermal part of the spectra. However, they could not explain the non-thermal part of the spectra. That's number one. The number two, that many terms were neglected. The advection terms and so on of the equation of motion was neglected. Therefore, it was also unstable, thermally unstable, and so on. So many things were there. So people move to thick disk. So thick disk means that it is not radiating all the matter, so it is storing some of the heat generated, and therefore it is puffing. If it is hot, if something is hot, it puffs up in the form of some torus, and it could produce the non-thermal radiation here, this non-thermal part of the radiation. However, it turned out to be unstable too. Okay, so if there is non-axisymmetric perturbations injected here, and people showed that it becomes unstable. It's called Papaluzzu-Pringle showed it. It's called Papaluzzu-Pringle instability. Okay, then there are many ad hoc models like lamppost model. So in black hole spectra of black hole binaries, and also in AGNs, people have seen iron K alpha line. Okay, a smeared iron K alpha line, and they propose that it comes because when you have a cool disk and it is producing some radiation, they are absorbed, and then again they get reflected from the disk, what was being generated, and there is some hot corona above. Okay, hot blobs of matter. So the radiation from the cool disk will be absorbed by would be intercepted by this corona, and they will radiate in hard X-rays, and those hard X-rays will also hit the cool disk below. And if there are iron atoms there, or iron nucleus there, atoms there, they will knock the one of the electrons from its orbit, and then there will be a K alpha transition. K alpha transition is the most favored transition of this knocking of electrons from iron atoms. So for that you need a cool disk, because the iron atom structure has to survive. Okay, very hot disk will not, the iron structure will not survive. So this is a very ad hoc model. But it could produce the iron K alpha line. The iron K alpha line should be a delta function, but it is being smeared because it is rotating. It will come as a horn because of the relativistic Doppler effect, and the other because the gravitational redshift of the frequency towards the black hole, it will also wash out a lot of part of it. So away from the black hole, this one horn will survive. Close to the black hole, that horn will not survive, and you will get some kind of a shape like this. But the downside of this, so these are the plus points and these are the negative minus points. The downside is that these kind of disk structure is not obtained from equations of motions, okay, and cannot account for hysteresis. Hysteresis is this thing we showed, right? The intensity versus time graph. Okay. Iron lines are also seen in white dwarfs, hardly a GR candidate. So this was touted initially as the model to show that black holes exist. All right. So magnetic jet models. So if you put some magnetic fields, we also have this jets. We're talking about the jets. So this Blandford-Payne model. Blandford-Payne model is a Payne model is very simple. Is that you have a Keplerian disk and you have magnetic fields anchored onto the Keplerian disk. How they do it, no one knows. But let's assume it can be done with suitably having current structures. current density structures, and then these are open field lines. Okay, so now if it is rotating, say it is moving in this direction very fast in Keplerian disk, the rotation is fast, so the foot points will move, okay, and the top half will lag behind, right? That will create a bending in the magnetic field. The magnetic field never likes bending, so what it will do, it will try to straighten up. Okay, so it will try to straighten up. Once it tries to straighten up, the electrons which are gyrating there will go like a slingshot. Okay, go out, and that's the proposal of Blandford-Payne about how to form outflows around black hole accretion disks. Okay, there are many problems here, but I'll come to that. Then the second one is Blandford's Dirac model. Blandford's Dirac model is if you have very low accretion and magnetic fields, this is you need a Kerr black hole for that. I've not talked about Kerr black hole at all. You have the ergosphere. Ergosphere is the region, without going into details, which co-rotates with the black hole. Kerr black hole is a rotating black hole. So there will be a region which the black hole forces the space-time to rotate with it. Okay, so there is no static observer within the ergosphere, and if the magnetic fields can enter these regions, they will be twisted, right? Okay, and once it twisted, the torsion will create the pointing flux, which will travel out, and as the pointing flux is being generated because of the rotation of the black hole. So it's a way of extraction of the rotational energy of the black hole, and this can, of course, this pointing flux can travel close to the speed of light, and the jets what we see, or the flash, I mean, we actually don't see the jets, we see the light going out, right? Brightness going out. So so they explained it that way. It can be easily understood, I mean easily calculated. Again, Penrose process is a variation of Hawking process. Okay, so it's like it creates a torsional Alban wave to propagate out, and it creates pairs, and one of the pair goes out in the form of jet. Okay, but people have done numerical simulations and found that this process is not very stable. Mathematically, all of them are very elegant models, but they do not suffice to say that they do not can explain the hysteresis curve, as we said again. Again, when Keplerian disk is dominant, there is no jet. That's what you've seen observationally. And neutral stars, even YSOs shows jet. They don't have ergosphere. Neutral stars are relativistic object. YSOs are non-relativistic objects, right? Young stellar objects. They don't need an ergosphere to generate a jet. Okay. So some of the neutron stars can generate jets with few Lorentz factor 3, Circinus. I forgot the name of the object. So so that's one of the down, what should I say, negative points. Why the models are historically partial arising out to solve the entire, most of these odd models, fluid equations in curved spacetime, aimed at addressing singular features and not the whole, taking the whole picture together, and the penchant to see the exotic nature of black holes. Okay, that is also there. So you have to sound sufficiently exotic in order to be taken seriously. Okay, so our take is that we take all the or most of the things that we can solve, take the whole set of equations and solve them. Okay, so I'm not going into details of this. So again, the jets that goes out, they will not be going out. I mean, the constant angular momentum surfaces are no more cylinders in GR, they are bent and so on. So all these things has to be taken if you want to do it theoretically, but you also can do simulations. This is one of the results that we show here. This is a featureless, this is like you can see it's smooth solutions, accretion solutions. These are theoretically obtained and along the equatorial plane, and these are the solid lines, and the circles are numerical simulations, and you can see that they agree well. But these kind of accretions, smooth accretions, don't show jets or QPOs. You see, we increase, this is inviscid, and we increase viscosity. So what viscosity does, it reduces angular momentum, and so therefore these are along the equatorial plane, and this is on the along the axis. Here the angular momentum is zero, so therefore the so viscosity has removed angular momentum along the equatorial plane, so matter can come to the equatorial plane and fall, but does nothing more. No jets, no QPOs, nothing. Okay. Here is a case where we have found accretion shocks. Here you see the high energy, high density region here, hot high density region, and they can form these jets. You can see these jets are coming out, and if we take the radiation from this region as well as this region, then we do an FFT, then we see that the QPOs. Okay, so if you have these hot regions there, then we can explain the QPOs. And if I'm not showing it here, if this oscillation is regular, then the QPOs are sharp and what is called the quality factor to be very high. And if the oscillations are not periodic, moving away from periodic, aperiodic, then they become broader. Okay, that's exactly what we see in observations. And also we also see that because it is this inner region is oscillating, the jet that are being flying out, there will jet on states and off states. In other words, we will be having blobs of matter going out, not a continuous jet. Okay, that's also seen in various observations. Okay, so here is a final simulation and showing that it is continuously spewing up a lot of jet, and it can easily reach it. This is around 200 Schwarzschild radius, and this is around 400 Schwarzschild radius. So it's a density plot, and you can see the almost we have fixed the boundary condition here. So this part is not changing at all, but the inner part you can see it's violet. Okay. All right. So just to summarize, I will just stop here. There are many things here. I have not touched many aspects here, but try to give an overall picture of what is black hole astrophysics. So we understand black hole systems better now, although many things are still unknown. Composition of the fluid that forms the jet and accretion disk. Our group is working on that at the moment, so it's not known properly. A link, and then link the composition with the spectrum and other things. So that's not well done as yet. The source of viscosity, the viscosity is phenomenological as still, but the source of viscosity is not well known. Generation acceleration mechanism of jets, again, people have done it, partially. It's as a patchwork, but not a whole full-scale, a holistic description of formation of jets and so on. It's not done. So the many things are yet to be done. In fact, generally the approach in astronomy, astrophysics is that you need more observation and more data analysis and so on. My opinion is that we need more theoreticians, okay, to understand the mechanism. Okay, with observations, of course, you need better observations. Without observation, astrophysics cannot run. But there are far too many observers than theoreticians, I can tell you that. And many things need to be done. Most of the models that have been developed over the last 2-3 decades, there are many loopholes there. Okay, a lot of things need to be done. Space plasma is a hugely complicated stuff. Okay, so we need brighter people, brighter students here. But in this talk, we have not discussed black hole astrophysics 4, that is the gravity waves, because you need a full talk to do any justice to the topic. And I have only touched the black hole astrophysics 2, but have not gone into details of it. That is the EHT experiment and so on. And that's it from me. Thank you. So I have to answer this, right? Okay. There's one question that the black hole has been detected in 1.3 millimeter, and that wavelength is very much affected by water vapor. Did it create any problem? It create many problems. It's not just water vapor. This there are other problems as well. Okay. So, for example, they just got one. I mean, this is 2017, right? Yeah, they did it in 2017, right? The launch was in 2017, right? I think so. So they published it in 2018. The paper. Yeah. So but after that, they have not been able to get proper solution. Okay, the weather needs to be very dry in those regions, and the weather needs to be uh, very good. Okay, that's if you go through the various videos they have created EHT experiment, that they will tell you, and in those videos, that it was a extremely lucky break they had, that in all these uh, 8 locations of the EHT telescopes, that they had a very good run of weather. Okay, so of course it will do, and therefore you don't get another snapshot, right, of the horizon there. Okay, so it definitely created a problem. Okay, what is the Cathy Bowman mysteries of? I have no idea about Cathy Bowman's revealing mysteries of black holes. Oh, so there are three questions here. What is the contribution of Cathy Bowman in revealing the mysteries of black hole? No, I have no idea. Hawking radiation has not. Okay, the second question is how Hawking radiation is measured. Hawking radiation has not been measured as yet. Hawking radiation, the temperature for Hawking radiation is less than the cosmic microwave background. So Hawking radiation will never be measured, okay, because it is below the temperature or the radiation scale that we see, the isotropic radiation scale, which is called CMBR, or cosmic microwave background radiation. Hawking radiation will never be measured. Okay? Hawking radiation is a very ingenious application of information theory, semi-classical quantum mechanics, and GR. Okay, some of the quantum gravity people also have some serious issues with it, but to me, it's a sheer genius from Hawking. That much I can tell, but it will never be measured. What are the advancements incorporated in Event Horizon Telescope after taking the first instrument? I have no idea. I'm not part of the Event Horizon Telescope. But what I hear is that they would like to have many more telescopes, so that so it's just 8 telescopes, right? So if you have an arm and you have just 8 regions, so there are many regions which are the gaps are too much between two telescopes. So to increase the resolution, they have to increase the number of telescopes. It's a big challenge. Okay, and then again, as the previous question that came from the previous the person with the previous question, is that there are many problems as well. Okay, you have to have in all these places worldwide at the same time. You have to have very good weather. So you have to be very lucky to get all those images. Third question, does every galaxy have a black hole? Can it be more than one in the same galaxy? There is no escape of light from black hole, then how there is some emission from it? So perhaps I have been able to answer some part of it. It's very difficult to say that whether every galaxy have a black hole or not, but now people do say that most galaxies have a black hole. So the central black hole in a galaxy is not formed by any, probably not formed by any stellar collapse. It has to be, collapse from during the formation of the galaxy itself. So the chances of every galaxy having a black hole is high, but you cannot be sure for that. Okay, there might be some galaxies without black holes. When there is no escape from light from black hole, as I said, that black holes do not emit anything. Hawking said about Hawking radiation, but that is a different issue altogether, and you will not be able to detect Hawking radiation anyway. The emission comes from the matter that is surrounding the black hole, that is moving around the black hole. Okay. We have the fourth question is why we have active galactic nuclei where supermassive black holes are at the center, and we see jet emission. Does the source of this jet is a supermassive black hole? The accretion disk responsible. First part of the question. Okay, sorry, I should read the question. Why the other question is why we have active galactic nuclei where supermassive black holes are at the center and we see jet emission. Does the source of this jet is the supermassive black hole or is the accretion disk responsible for it? Again, I tried to answer them in the talk. Why active galactic nuclei with supermassive black holes? There is no reason for that. Okay, active galactic nuclei can be, I mean, AGNs comes with, sorry, I misunderstood the question. Because if you have to have a black hole at the center of a galaxy, it has to be big. Okay, it cannot have a 10 solar mass black hole at the center of it. Because even if you have started the 10 solar mass black hole, which is unlikely, I have not worked out the length scale that will take to grow within, say, a few tens of million years to form a supermassive black hole. However, but if you essentially, as I said, that AGNs, the supermassive, the black holes at the center of galaxies were formed probably during the formation of the galaxy itself. Okay, so the matter as it forms, so much matter, and if there is a seed black hole that generates there, it will quickly generate a supermassive black hole by accretion. Jet emissions. So, for example, our galaxy is not an AGN, right? But it has a supermassive black hole at the center. Jet emissions, for the formation of jets, as I said, that you don't need a black hole to form a jet. Okay. And now there are other school of thought, especially Mackenzie and mostly coming from America. They support that the relativistic jets around black holes are formed by the Blankford-Snag mechanism. They do, but there are other people who even observationally have challenged it. Okay, how do we measure the spin of the black hole and its direction of rotation? Now, it's a big question. The spin of the black hole, there are many ways of doing it. Some people do it from the spectra itself, but one must understand there is some kind of degeneracy between mass and spin. Okay, you can go up in this mass and explain the observations that we have now. Okay, even better observations will need to. There will be a breaking of degeneracy within mass and spin, and smaller mass black hole with larger spin can give the same sort of observational result. There is one way of doing it is when it is in the in the soft state where you have a dominant thermal radiation. If I can go back, can I go back? So yes. So this is the yes. This is the soft state for Cygnus X1 actually. So you have so you have a dominant thermal radiation which comes from the Keplerian disk as we discussed. So that has an analytical form, and so as you increase the spin, the marginal stable orbit, which is the edge of the Keplerian disk, also comes closer to the horizon. So if you can model that and keep spin parameter as an input, then you can supply the spin for which this part fits perfectly well, and then you can get the spin parameter. That's one of the way of doing it. Is Schwarzschild limit of black hole gives the clues of singularity? Okay, there's one question: is Schwarzschild limit of black holes gives the clues of singularity? I do not understand the question properly. Do you mean to say that the are you talking of the central black singularity of the black hole? Okay, yeah, just for other viewers, so if you look at the yes the line element of Schwarzschild metric, you see that uh, you see there are two. So this one blows up, right? At r equals to 2gm by c squared. That's what we said. But it can be transformed away. I mean, if you use Kruskal coordinates, it can be shown that on the horizon this part does not blow up. Okay. So if it is an essential singularity, then no form of frame transformation will be able to get rid of the singularity. This is what is called the coordinate singularity. It's a wrong choice of what can say that the wrong choice of coordinates what we have taken. It's not valid in the from black hole horizon inside. And but you see, if it r is equals to 0, that's r equals to 0 point, it is actually a singularity. No amount of frame transformation can get rid of that. So that resides at the center, and Schwarzschild radius or the event horizon actually covers it. But I don't understand the question properly. So if you can send another question, I can take it on and I can send you. If you send the your email Sanjeev Devnath, I can send you a reply. Why are jets perpendicular to the accretion disk? Okay, the reason is simple, right? So like if you look at the one simulation I just get. Oh, by the way, it's not always perpendicular, it's locally perpendicular. What I mean, okay? Like for example, in this case, I have this simulation, I have forced up-down symmetry here. If I have not put in forced up-down symmetry, then it could have this thing could have been bent. Okay. If that is bent, then this is still the equatorial plane, but I will see the jet is coming in a not in perpendicular direction. It will be in a oblique direction. But the reason locally it is perpendicular is because the matter is coming from here, right? Even if whatever pressure and whatever thing we are creating, you see this matter is trying to go out, but it cannot because there is a constant supply of matter from here. So the only free space left is this direction. So it goes in that direction. As simple as that. As the black hole, there's another question. As the black hole sucks up the matter, the size of the black hole increases, but at the same time, Hawking radius reduces the size. Why the contradiction? Is it because the black hole takes too long to evaporate? See, if this, I mean, astrophysical black holes are the size of few solar mass to tens of solar mass, and even very large million solar mass, billion solar mass. And for that, black Hawking radiation, if true, is very, very, very small. Okay, it's negligible. So so there is actually, for astrophysics, astrophysical black holes, there is no such problem. However, if Hawking radiation is true, that is the the bit of genius that Hawking showed in merging general relativity, information theory, and then semi-classical quantum mechanics. The ingenuity he showed, if it is true, if it holds a proper quantum gravity calculation, then one can say that if you can actually create very small black holes, okay, then it will be an interesting question that which will win, whether accretion will win or evaporation will win. But for astrophysical black holes, it's not a contradiction at all. It's, even if Hawking radiation is true, it nowhere matches the accretion, the input of energy from the accretion. Okay, so why mini black holes evaporate faster than the massive black holes? Because the rate of evaporation is inversely proportional to the black hole mass. That's what you get. What would happen to our planet when there is quasar formation in the center of our galaxy? Is it related to the size of the black hole in our galaxy? No, it's not related to the size of the black hole of our galaxy. For example, it's a um, uh, 10 to the power 6 solar mass, the size of the black hole in our galaxy, okay? And we are far, far, far away. 10 to the power 6 solar mass means its gravitational radius is, it would be like 10 to the power 6 kilometers, okay? Right? And we are, how far are we? 12 kpc, right? Around 12 kpc from the center of the galaxy. Okay, but it's definitely it's more than 8-9 kpc. I have forgotten exactly how far are we. 8 kpc around. So that is, yeah, kpc means it is 10 to the power 21 centimeter. That means 10 to the power 16 kilometers. Okay, far away from the center of galaxy. So the GR effect of the central black hole on us is non-negligible. However, if a quasar forms and the jet is directed towards us, okay, then we have a problem. Okay, and if someone misses today's live lecture, they can find it in ARIES Facebook page and also on ARIES YouTube channel. The links to these sites is available on the ARIES official site. You can also submit your questions later on and also provide your feedback by using the link available below the videos. Okay, thank you very much.